finished it. Okay, our next speaker is Dr. Kimin Lee from UC Berkeley. He finished his PhD from KAIST and now he's doing his postdoc at UC Berkeley. And I think he recently gave a similar talk at AI Summer School, right? And so I think it will be a good opportunity for those who have missed it, and also including myself. And it will be an exciting talk to listen. The title would be Toward a Tractable Solution for Human-in-the-Loop Reinforcement Learning, Algorithmic and Benchmark. Okay, so please go ahead.
Cool. Yeah, thank you for the nice introduction. And I think my internet connection is a little bit unstable, but let me see. Can you hear me?
Yes, I can hear you.
Okay, cool. Let me know my connection is unstable. Okay. Hi, I'm Kimin Lee. I'm a postdoc working with Peter Abil at UC Berkeley. And thank you for having me today. In these presentations, I'm going to talk about research topic that I studied during my postdoc. So the first half of the presentation is about how to teach agents via reinforcement learning, shortly RL with a human feedback. And the second part is about how to efficiently train RL agents from the pixel observation. So I'm going to cover the joint work with the following collaborator from inside and outside of the Berkeley. And if you have any question during the presentation, please don't hesitate and just let me know via chat or by turning on your microphone. All right, then let's get started. First, to make sure that we are on the same page, let me briefly introduce what is the reinforcement learning. So reinforcement learning is a framework to solve the sequential decision-making problem. So as shown in this figure, RL consists of environments and agents, and every time step, agent produce some decision based on the current state. And as a result, environment provide the next state and reward. Then by doing an interaction with the environment, agent generates a rollout which corresponds to the sequence of state, action, and reward. And the goal of the reinforcement learning is to find some optimal policy which maximizes the generated sum of the reward as shown in this equation. So we can apply RL to various problems based on how we define state, action, and reward. So for example, if we define robot configuration as a state, motor control as an action, and the distance to the target object as a reward, we can use RL to control the robot. And if we define game screen as a state, joystick command as actions, and score as a reward, we can train RL agents to solve the video game. And we can also use RL to obtain language model by defining conversation so far as a state, next reply as an action, and customer satisfaction as a reward. And in the last figure, by incorporating deep neural network as the policy or dynamics model, deep reinforcement learning has been successful in a diverse number of the domains. For example, in 2013, DeepMind achieved the human-level performance on the Atari games by modeling cube function as deep neural network. And in 2014, Berkeley showed that we can solve the continuous control task by proposing on-policy method like TIPO method. And in 2015, DeepMind released the AlphaGo, which mastered the game of the Go and defeated the Shadow Lee, who was the smartest Go player in the world. And after that, OpenAI and DeepMind showed that RL can be also applied to very complex video games like Dota 2 and StarCraft. And also it is well known that RL can be applied to more practical applications like robotic manipulation. For example, OpenAI shows that RL can be very precise, RL can be do the very precise robot control like solving Rubik's Cube. And the startup company from our lab called Covariance is using reinforcement learning to control the real robot in the warehouse. So these examples are really impressive and clearly show the potential of the deep reinforcement learning. However, at the same time, there are several problems in deep reinforcement learning. And in order to understand more detail, let me talk about the typical pipeline for reinforcement learning. First, Under the assumption that action is well defined, we need to set up the state estimation system to understand where are the most important entities in the world, using some sensor or some vision systems like pose estimation, motion capture, and so forth. Then once we define the state, we need to also define the reward that represent our target task. And as a final step, we train RL agents using various RL algorithms like PPO, TIPO, SEG, Rainbow, and so forth. However, problem here is that it is extremely hard to do everything in this pipeline in every environment we encounter. So specifically, let's think about reward engineering first. Basically, the fundamental problem of the reward engineering is that it requires domain expertise to define the reward. And there are many tasks where we cannot easily define the reward. For example, if you think about cooking or cleaning, it is non-trivial to quantify the taste or cleanliness. And because of that, it is hard to define, hard to use deep reinforcement learning or reinforcement learning. Also, if we don't carefully design the reward function, RL agent has the tendency to discover the way to achieve the high reward, high returns by learning the unexpected and unintended behaviors. For example, the goal of this Ghost Runner game is to win a race, and although the reward is defined to be the player's score, the agent discovered the loophole in the game and achieved the high score by circling as shown in this video instead of reaching to the our finish line. So generally speaking, it is a bit hard to incorporate the desired behavior in the reward function. So from the next slide, I'm going to introduce my recent works to solve the problem of the reward engineering. And the first paper is Pebble, which is the joint work with Laura Smith and Peter Abel. Okay, so as a solution to overcome the reward engineering, in this paper, we focus on preference-based reinforcement learning. So in this framework, we don't assume that agents receive the reward from the environments. Instead, the agent asks teachers' preference about the two behavior and use this information to run some tests. So basically, we didn't assume that there are predefined reward which quantify the progress of our target task. And since human can provide some feedback based on the intuition, one can apply RL to more harder tasks by using this human-in-the-loop reinforcement learning framework, where we cannot easily define the reward. Also, we can avoid reward exploitation because we can interactively guide the agent according to their progress. However, involving human in the loop puts very large burden on the human. Actually, you might not want to use this framework if you have to spend huge amounts of time to teach our agent. So this implies that we need to think about how to design very feedback efficient algorithm to utilize this idea. And as a solutions, we propose Pebble, which consists of two main ideas. As shown in this animations, Pebble is based on the unsupervised pre-training and open policy RL with relabeling. And I'm going to explain more detail from the next slide. Right, the first idea is unsupervised pre-training. First, we note that we found that in the beginning of the training, a naive agent executes a random policy, and the behavior from the random policy is usually hard for human to judge. So this video is the behavior generated by random policy on the Hopper agents. And as you can see, the behaviors are very static and meaningless. So because of that, it requires many human feedback for this method to show the initial progress. So we think about the following research question: how to make our agents show meaningful behavior without additional supervision at the beginning. As a solutions, we pre-train our agents based on the state entropy maximization. Specifically, we define entropy of the state distribution as intrinsic reward and force our agents to maximize it. Then in order to have a high entropy, as shown in this example, our agent needs to explore the environment dynamically And by doing so, we hope that our agents can learn some more meaningful behavior and more dynamic behavior by maximizing the state entropy. However, the challenge here is that measuring the state entropy is computationally intractable. So to handle this intractability, we use the k-nearest entropy estimator proposed in the 2003. First, because it is hard to compute the expectation, we store visited state in some buffer to approximate the expectation, which basically correspond to the sampling. And instead of computing log likelihood, we compute the distance between each state and its k nearest neighbor because we don't know the state distribution. Then we can induce our approximation as is shown in this equation. So the intuition behind this equation is that the distance between k nearest neighbor would be higher as the agent visits more diverse set of the state. So using this state entropy estimator, we encourage our agents to explore the environment without any supervision. And here is a qualitative example of the difference between the naive agent versus unsupervised pre-trained agent. So one can easily note that after pre-training, the agent shows more meaningful behaviors like jumping and flipping. And intuitively, this agent should be easier for human to teach locomotion tasks than before. So that is the high-level idea of the unsupervised pre-training. And any questions so far? Okay. Then let me move on to the second idea, the open policy RL without relabeling. Basically, the preference-based reinforcement learning consists of the following steps. First, we collect some sample which correspond to the state, action, and next state by interacting with the environment and store the sample into the buffer. And once we have some amounts of the training sample, we choose two behavior from the buffer and ask a human's preference. Specifically, the behavior is a segment of the trajectory, which correspond to the 1 or 3 second video clip, and human provide a binary label to indicate their preference. So as shown in this example, the label becomes 0,1 if the human prefers the working behavior using the both stack. And after collecting human's preference, in order to utilize reinforcement learning, we run a reward model, which is aligned with the human's preference. So here is the detail about reward learning. Basically, we have a training data, which consists of 2 segments and binary label from the human. And our goal here is that is to run the reward model, which produces the scalar value given state and action. Here, the important thing is to align this reward model with the human's preference. And to this end, we formulate this problem as binary classification. So specifically, we first define a preference predictor as shown in this equation by following the Bradley-Terry model. So this model assumes that the probability of preferring a segment is proportional to the exponential sum of the reward over the segment. So for example, event that human prefer the segment 1 is proportional to sum of the reward over the segment 1. And in this way, we can define some binary classifier which predict the preference based on our current reward model. Then we can align our reward model and human's preference by training this preference predictor via standard cross entropy laws. So basically, we just hope that by aligning this preference predictor with the human's preference, our reward model can capture the human's intention into the our reward model. So that is the main idea of the reward learning. And any question about this part? Because I think this part is a kind of key components in our paper. So let me know if you don't understand this part. Okay, and once we have a reward model, actually we can optimize the policy using open policy RL method like soft-vector query. However, here one caveat is that reward model is changing over training time. So because of that, training can be very unstable because the previous experience are labeled with the previous reward model. So to overcome this limitation, we introduce simple solutions which relabels all experience in the buffer every time we update the reward model. And by utilizing this simple idea, we found that we can optimize the policy using open policy RL method very simple and feedback efficiently. And this is the core idea of the policy optimizations. And by repeating step 1 to step 4, we can interactively train RL agents using humans' preference. So here is the summary of our method. First, because random policy doesn't show the meaningful behavior, we do the unsupervised pre-training, then agents show more meaningful behavior. Then we ask humans' preference, and based on the preference, we update our agents. Then using this, preference, our agent runs something, and then we collect the new behavior, and then ask the humans query again. So by repeating this interaction, one can note that our agent runs some more, meaningful behaviors like crawling, standing, and working at the end. So yeah, as you can see, currently, our agents know how to stand based on the human's preference. And by providing more preference, actually our agents can walk like this. So that is the core idea of the Pebble. And any questions so far?
Can I ask one question?
Yeah, sure.
So you said the humans are providing the preference labels, but then maybe they should also have, they should know the goal of this agent in mind. So are that also given to the labelers? I mean, how do you determine, how does a labeler determine which is preferred to other? Because they need to know the goal of the.
So it is totally depends on humans' intention. Like if I wanna teach the walking behavior, maybe I'm gonna provide a preference to the more, behavior very similar to my desired behavior given the query from our agents. Like query correspond to the two behavior. So yeah, basically it is already.
Okay, so the goal of agent is also not given to the human labeler. So then it means depending on which human gives the preference label, the agent will learn different things.
Yeah, exactly. So actually in this framework, the goal itself is defined by the agent, the teacher.
Okay.
So depends on who is the teacher, the learned behavior can be different, and yeah, and so forth. Yeah.
Okay. So then in this work, how did you evaluate the end product, end result?
Yeah, that's really a good question. Actually, in this framework, because we don't know the ground truth reward or ground truth goal of the human teacher, it is already hard to evaluate the performance, right? So that is the reason why in the second paper, I'm gonna talk about designing some benchmark to study this direction. So in short, it is already hard to evaluate the behavior from the real humans, but I'm gonna talk about some benchmark which is based on the simulated teacher. And in this case, we can define some evaluation metric. So I'm gonna also talk about the parts, but that's really a good question, actually. Yeah.
Okay.
Cool. And any other question about the method? Right, then let me move on to the experimental result. First, we verify whether we can teach the novel behavior using our method. So using 200 query, less than 30 minutes, we teach the quadruped agent to wave its front leg. The thing to note here is that we can teach our agent to perform variation of the same task. So the agent on the left wave is left front leg, while the agents on the right wave is right front leg. So this implies that we can actually control agent according to our preference. And we also show that we can teach the hopper to perform the backflip only using 50 queries. Here, I want to remark that defining a reward function for backflip is non-trivial. So these experimental results shows that we can teach novel behavior without well-defined, well-engineered reward functions. Next, we evaluate the claim that we can avoid reward exploitation via preference-based reinforcement learning. First, as shown in this video, we found that worker agent trained with a predefined reward achieved the maximum return using a strange and unnatural way. So basically, it is working only using a one leg. This is because the predefined reward from the benchmark is only based on the velocity of the agent. So it is hard to guarantee that our agents can work in a natural way by maximizing the predefined reward, as shown in this example. However, we showed that worker agent trained with a human preference can work in a more natural and human-like manner, as shown in this example, because we provide a preference to the such behavior. So these kinds of the experimental results show the potential of the preference-based learning to avoid reward engineering and reward exploitation. So here is the take-home message from the first paper. So basically in this paper, we showed that feedback efficiency of the preference-based reinforcement learning can be improved by utilizing the unsupervised pre-training and open policy reinforcement learning. And using this framework, we can do reinforcement learning without reward engineering, and we can also avoid reward exploitation. So that's it for the first paper. And any question about Pebble? Okay. Right, then let me talk about the next problem. So when we studied preference-based reinforcement learning, unlike other RF problem, there was no standard benchmark. So because of that, it is a little bit hard to compare the algorithm and quantify the scientific progress. So we think about the following research questions. Can you design a proper benchmark for the preference-based reinforcement learning? And by benchmarking the existing method, can you find some interesting future direction on the preference-based reinforcement learning? And to answer this question, we propose BPREP, a benchmark for preference-based reinforcement learning, which is a joint work with Laura Smith, Anka Dragan, and Peter Abil. First, let me explain what is the key challenge in designing a benchmark for the preference-based reinforcement learning. Basically, utilizing real human input for training and evaluation is ideal. For example, we can think about using Amazon Mechanical Turk to get some real human feedback for this benchmark. However, there are several problems in using real human feedback. First, it is hard to define evaluation metric because we don't have ground truth access to the human's reward function. At the same time, it is hard to evaluate the method very quickly if we use the real human input. So as a solution, we designed a simulated teacher with various relationality. So here is the detail. First, we focus on solving the existing RA task where the predefined reward is available. But instead of directly utilizing the predefined reward, we generate preference using simulated teacher. So as shown in this example, given two segments, the simulated teacher compares the true task returns and provide a preference to the segment with a high returns. Then there are two main advantages from this simulated teacher. First, we can do experiments very quickly because this simulated teacher can generate the preference immediately. Also, we can evaluate the agent quantitatively by measuring the true task return because the preference is directly based on the true task reward. So I hope that this can answer to your question, the previous question, by the way. So, but at the same time, there are some issues on using an ideal teacher. So if we evaluate the performance only using an ideal teacher, which always provide a perfect label, actually it is a little bit unrealistic. And because it is quite well known that real humans are not perfectly rational. So for example, human can make a mistake as shown in this animation, and teaching style also can be different. Some teacher can be very generous, while some teacher can be very strict, right? So I think it is also relevant to, Professor Tesamu's question about depend on who is the teacher, actually the results also can be different, right? So to design more realistic model of the human teacher, we can add some functionality to this simulated teacher. The first functionality is keeping the query. Basically, if both behaviors are meaningless, a teacher don't want to provide a preference. So we skip the query if both behaviors are bad. So basically, we just introduce some threshold, and the sum of the reward is below the threshold. We just, skip the query. And the second functionality is providing a uniform label. One can imagine that there are some cases that both behaviors are equally good, and making them as equally preferable can be better. So we model this behavior by providing a uniform label, 0,5, 0,5 as a response if both segments have a similar sum of the reward. So basically, we measure the difference between, sum of the reward over the two segments, and then if the difference is below some threshold, we just provide a uniform label. And we also flip the preference with probability of the epsilon, because human can make a mistake. So we randomly change the preference by flipping a coin. And there are more relationality like myopic behavior and stochastic response, but please check out the paper for more detail. So we incorporate these kinds of the functionality into this simulated teacher and evaluate our method with various simulated teacher with various, by changing some hyperparameter for these kinds of the functionality. Right, so using this simulated teacher, we benchmark the recent preference-based reinforcement learning algorithms like Pebble and Preference PPO in this paper. However, due to the lack of time, I'm gonna only talk about results using Pebble on quadruped and sweep into I wanna provide the main observation through using this experimental result. First, as an evaluation metric, we measure the relative performance with respect to the SEG with a true task reward. So we measure how much we can achieve by using a preference from the simulated teacher. And here, the red bar corresponds to the relative performance of the Pebble on the ideal teacher, which always provide a clean label. And blue bar corresponds to the performance on the noisy teacher, which provide a wrong label with 10% probability. And one can note that Pebble suffer from the poor performance when teacher can provide a wrong label on both environments. Yeah, so basically the performance on the ideal teacher is above 80%, but if the teacher provide a wrong label, the performance is decreased by 20% or something. So this implies that current preference-based reinforcement learning is not robust to the noisy teacher, and we need to do more investigation on improving the robustness. So in the reward learning, I think we need to incorporate some technique from the, from handling noise label in supervised learning. And then by doing so, I believe that we can maybe improve the robustness of our preference-based learning method. And we also found that providing uniform label to equally preferable segment, which correspond to the blue bar here, is more useful than relying on the perfect label. So this is because providing uniform label can be interpreted as applying some regularization like label smoothing. So this just implies that preference-based learning can be improved by studying effects of deregularizations like dropout, regularization, and so forth. Any question about the experimental results so far? Okay. So here is the take-home message from the second paper. In this paper, we present a benchmark designed for preference-based reinforcement learning. And even though I skipped the many things in this presentation, but actually there are more contents like benchmarking existing method and analyzing the effects of the algorithmic design choice in the paper. So please check out the paper if you are interested in such results. And here are some summary of our main observation. So first, we found that current algorithm is not perfect, and there are many issues like handling noisy label. And we also found that current method is very sensitive to the various algorithmic designs like how to generate the query and feedback scheduling. So I hope that BPrep can be a common starting point to study preference-based reinforcement learning, and hope, maybe by utilizing this benchmark, we can make more progress on this direction. Right, so that's it for the second paper. And any question about the benchmark? Okay, then do you have any question or?
Actually, can I ask one more question?
Sure, yeah.
So I think the Pebble algorithm, it kind of tries to somehow estimate the actual reward function that is consistent with the preference labels, right?
Exactly.
Then your RL algorithm is just the standard methods that try to maximize that estimated reward. Is that right?
Yeah, but actually, I also want to point out something. So basically, unlike standard reinforcement learning, reward is not fixed, and there is some kind of the non-stationarity in the reward function, right? So that is the reason why many previous methods utilize the own policy method, but we found that if we use the own policy method, the sample efficiency is really bad. And because of that, it also requires more feedback from the human. So that is the reason why we think about utilizing the open policy reinforcement learning. But problem with the open policy reinforcement learning is that actually the sample in the buffer is labeled with the previous reward model, right? So it is a little bit non-trivial, not straightforward to utilize the open policy reinforcement learning for this problem. So we try several techniques like relabeling, and actually we also try something like a reset the Q function and our policy when it updates the reset the Q function, only the Q function when it updates the reward model. But by utilizing the simple techniques like relabeling, we found that we can utilize the open policy reinforcement learning in a very stable way. And I think that is the one. I think underlying RL is same, but I just want to mention that if we think about the utilizing open policy reinforcement learning, it is non-trivial, but we just provide some technique to utilize the existing RL method for this problem. I mean, for this preference-based learning, and is that that is okay, cool.
Yeah, so I guess this is just a vague question, but maybe I was wondering, so this is so you're doing this learning in 2 steps, right? You first learn the reward
Exactly.
estimator, and then use that in off policy learning.
Yeah.
Would there be some possibility that you do this like one shot? For example, you take you sample 2 episodes from the buffer, and then somehow try to learn the agent without explicitly estimating this reward, but just try to match the preference label, something like that.
Yeah, that's a good question. Actually, in the preference-based learning, there are several methods. Like I only talk about running a reward model, as you mentioned, actually we can also think about different directions, like maybe something like following the demonstration, not a demonstration, but prepared, trajectory, and then similar to the, imitation learning or, inverse reinforcement learning, we can think about different direction. But as I know, this learning or reward model is most stable and very effective compared to the other method. So as you mentioned, there are other directions, but currently many people utilize this reward learning because it's very easy to obtain the good reward model using hereditary by following the hereditary model. But that's a really good question. And I also want to remark that there are so many ways to do the human in the loop reinforcement learning, even though we didn't talk about everything, but there are many ways. And actually I tried several directions when I started this project, but I just found that this preference-based learning is most stable to learn something. But I'm also interested in other direction in the human in the loop learning, like using a different feedback, like maybe text or something like good or bad, something like some binary value. But there are so many directions in this domain.
Okay, thank you.
Okay, cool.
Can I ask a trivia question?
Sure. Any question is welcome.
So you mentioned about the uniform label in simulating human teachers in BPrep. Was there no uniform label in the Pebble?
Actually, we also utilize the uniform label when you use the real human. When you train our agents using a real human input, like human can provide the uniform label when you try the Pebble, actually.
So the experiment about the uniform label was it almost reached the baseline, right?
Yes. So, that was our finding.
We can say that it almost resembles the real human teacher. Can you think like that?
I'm not sure. So actually that's a really good question. Actually, when you submit this paper to the dataset benchmark track at the NeurIPS, and reviewers also point out similar things like, so we propose some simulated teacher, but can you guarantee something about it? Some simulated teacher is really closer to the real human or not? But I would say it is a little bit hard to say something about that part, because depending on who is the human, actually the trend is very different, and we cannot guarantee whether some types of the simulated teacher is indeed close to the real human or something. But we just want to use this framework to make a very robust preference-based reinforcement learning method, which is very robust to the different types of the teacher. And by obtaining such algorithm, we hope that maybe that algorithm also can be robust and very effective to the real human. But I would say it is a little bit hard to guarantee such things.
Okay. Thank you.
Okay. Cool. Any other questions about preference-based learning? I think any question is good, but okay. Feel free to let me know if you have a question. Then let me go back to the typical pipeline in the reinforcement learning. So far I talked about human in the loop reinforcement learning to handle the problem of the reward engineering. But I also want to remark that there is some problem in the state estimation. Basically, state estimation is usually expensive to implement. So for example, as shown in this table, OpenAI used many informations like fingertip positions, the cube position, and cube orientation to solve the Rubik's Cube. And one can imagine that we need some special sensor to obtain such information. And this makes it hard to use the reinforcement learning to many applications. So to solve this problem, last year, I focused on how to do reinforcement learning directly from the pixel observation instead of utilizing the state information. Because pixel observation is very easy to obtain and using a camera device, and vision-based reinforcement learning is very important to apply RL to many applications. However, there is some problem in vision-based reinforcement learning. The problem is that RL becomes extremely sample inefficient when inputs are very high dimensional. So let's look at this example. The plot on the left shows the two types of the learning curve of the walker. So the blue curve is learning curve of the state-based DPOPG method, which correspond to the one of the state-of-art, RL method, and the green curve correspond to the performance learning curve of the pixel-based DPOPG method. So everything is same. RL algorithm, task, agent is same, but only input is different. And one can clearly note that pixel-based agent needs 50 million more training sample than state-based method to perform the same task. And actually, final performance of pixel-based method is much worse than performance of the state-based method. So we think about the following question. Can vision-based reinforcement learning achieve the same sample efficiency as state-based reinforcement learning? So in other words, we want to reduce the gap between this blue curve and red curve as shown in this example, as shown in this figure. So we studied this direction very actively last year, and we found that applying techniques from the computer vision to reinforcement learning is very important to solve this problem. So this graph shows the median evaluation score across the 6 locomotion tasks at 100K time step, which correspond to the blue bar here, and 500K time step, which correspond to the red bar here. And as you can see, the pixel-based object critic is really inefficient compared to the state-based object critic. But first, the paper from our group called CAR found that adding contrast with learning to RL objective function can improve the sample efficiency of the reinforcement learning. So as shown in this figure, CAR just adds some contrast learning to update our imaging encoder. And by doing so, we must match the performance of the state-based method as shown in this figure. And actually, in the next paper, we also found that only utilizing the data augmentation can be enough to improve the performance. So as shown in this bar graph, we match the performance of the state-based method by only utilizing a data augmentation. Because data augmentation is kind of implicit regularization based on the reward signal from our environment. So because of that, we found that data augmentation can induce more RS specific representation to our encoder, and such representation can be much more useful to improve the sample efficiency of our method. So these two papers, the main insight from these two papers is that actually by utilizing the existing method from the computer vision, we can also improve the sample efficiency when you apply RL to the pixel observation. And in our recent paper called e-TEC, actually we think about what is the limitation of the curve, and we found that we didn't incorporate the temporal information in the representation learning. So we propose a new representation learning, which combine contrast learning, which applies the contrast learning to the temporal input, and found that e-TEC also can improve the performance of the reinforcement learning on various vision-based environment. And we also studied the exploration method called RE3, which maximizes the state entropy using random encoder. And by utilizing this idea, we found that we can further improve the performance of this vision-based reinforcement learning even on the sparse reward environment. So yeah, that is the very quick summary about the RL from the pixel. And any question about this part? Okay, then here is the conclusion. Basically, I study human in the loop reinforcement learning and added from the pixel to solve the problem in doing the reinforcement learning. And I believe that such direction can be useful to scale up the reinforcement learning to a more challenging domain. So yeah, my research goal is applying reinforcement learning to more diverse, challenging, and yeah, various application. And in order to do that, actually, I'm studying various axes in the reinforcement learning. Cool. So that's it for the presentation. And I do like to thank my collaborator and everyone listening for your attention. And yeah, let me stop here. And yeah, let's have a Q&A session.
Okay. Thank you very much for the exciting talk. Is there any questions? 채팅으로 남겨주셔도 되고 직접 물어봐도 됩니다. 아까 전에 그 유니폼 뭐 그 티처를 시뮬레이트 하는 거에서 이제 퍼펙트 티처를 했을 때랑 그 다음에 유니폼 레이블을 추가했을 때 그게 거의 그 1, 그러니까 노멀라이즈 스코어로 1을 달성하는 게 있었잖아요.
네네.
그게 그러니까 제가 아까 그 부분 잠깐 놓쳤는데, 그러니까 정확하게 리워드가 똑같을 때 그 유니폼 레이블을 주는 거였나요?
아니요, 사실 그 디테일은 제가 발표에서는 말씀을 드리지 않았는데, 실제로는 어떤 트레스홀드 같은 거가 하이퍼 파라미터로 존재하고, 디퍼런스가 그 트레스홀드보다 작을 때 이제 유니폼 레이블을 주는 형태로 임플리멘테이션이 돼 있고요. 사실 그 트레스홀드를 어떻게 주냐에 따라서 사실 티처의 그 프레퍼런스를 주는 그 티칭 스타일 같은 게 달라진 형태로 지금 디자인이 되어 있고, 네, 사실은 그 결과가 오히려 더 메이크 센스한 게 항상 이제 아이디어 티처는 예를 들어서 리워드가 조금 좋아도 그거가 좋다라는 식으로 이제 줄 테니까 사실 일종의 오버피팅 같은 게 일어나겠죠. 그렇기 때문에 사실은 그런 샘플들에서 에 대해서 유니폼 레이블을 줌으로써 오히려 더 휴먼 인텐션에 얼라인된 그런 그 리워드 러닝이 가능한 거를 사실 그 유니폼 티처를 통해서 저희가 볼 수 있었고, 네. 그렇기 때문에 좀 더, 네.
그렇게 하면은 퍼펙트 리워드 펑션으로 학습한 그 에이전트의 리워드를 동일하게 달성할 수 있다. 그게 결과였나요?
네. 근데 이제 한 가지 더 말씀드리고 싶은 건 모든 인바이러먼트는 아니고 저희가 실험한 아주 이제 간단한 인바이러먼트들에서는 그러니까 인터액션을 충분히 많이 줘서 이제 그 샘플 이피션시를 이그노어하고 파이널 퍼포먼스만 봤을 때 충분히 어치브 할 수 있다. 왜냐하면 이제 저희의 메인 포커스는 피드백 이피션시, 피드백을 얼마나 줬을 때 실제 매칭을 할 수 있는가가 궁금하기 때문에 우선은 그런 식으로 매저를 했고요. 실제 그래프를 보시면은 당연히 이제 샘플도 더 많이 필요하고, 그러니까 이제 샘플은 인바이러먼트 인터랙션은 더 많이 필요하고, 하지만 이제 리워드 러닝 자체는 충분히 잘 동작할 수 있다라는 거를 실험에서
그것도 약간은 좀 놀라운 결과 아닌가요? 이게 그러니까 정보를 사실 훨씬 적게 주는 건데 정확한 에스티메이션이 그냥 잘 된다라는 건가요? 어쨌든.
네, 저희가 테스트한 실험한 환경에 대해서는 가능한 걸 보였고요. 한 가지 더 노트를 드리면 사실은 더 어려운 환경도 저희가 해봤는데 잘 안 되고요. 그리고 뭐 예를 들어서 로보틱스 매니플레이션 태스크 같은 경우는 피드백이 엄청 많이 필요합니다. 예를 들어 로코모션은 한 피드백을 한 500개만 줘도 충분히 이제 그런 리워드가 잘 얼라인 돼서 좋은 성능이 내는데, 예를 들어서 로보틱스 환경 같은 경우는 뭐 10K나 더 훨씬 많은 20K 정도 줘야 뭐 매칭이 되는 경우도 있고, 그래서 물론 발표에서는 많은 디테일이 놓쳐져 있고 뭔가 다 동작하는 것처럼 돼 있지만 실제로 페이퍼를 보시면은 저희가 그런 것들에 대한 디스커션도 많이 했거든요. 그러니까 너무 챌린징한 도메인에서는 아직도 많이 필요하고 사실 그런 것들을 핸들링하기 위한 테크닉들이 많이 필요하다는 걸 네,
네.
남겨두었습니다. 네.
혹시 또 질문 있으신가요? 그냥 제너럴하게 그러니까 RL이 되게 프로미싱하다 이제 그런 앞에 처음에 그렇게 이제 시작을 하셨는데
네,
사실은 또 이제 그러니까 그런 게임 도메인 이런 시뮬레이션이 가능한 도메인에서 이제 결과들이 주로 많고
네.
그러니까 진짜 아까 그 로봇 뭐 매니플레이션 얘기도 하셨는데 이제 진짜로 인더스트리에 지금 적용이 되는 그런 예가 있나요? 아니면 아직
네, 그래서 우선은 인더스트리에 적용되는 예 같은 경우는 사실 저희 교수님이 지금 스타트업을 하고 있는 코베리언트가 제일 좋은
네.
예인 것 같은데 실제로 사실 이제 그 스타트업 컴퍼니에 대해서 디테일은 많이 알려주진
네.
않지만 이 회사는 진짜 RL을 써서
네.
이제 로보틱스 매니플레이션 같은 걸 하고 있고 이제 이 회사가 포커싱하는 건 약간 막 오브젝트 모양도 바뀔 수 있고 그러니까 사실 로지스틱에서 로봇을 쓰는 경우는 많지만 완전 컨트롤된 인바이러먼트에서 스트럭처된 인바이러먼트에서만 하고 있는데 사실 제 생각에 이런 딥러닝이나 머신러닝 기반 메소드들은 약간의 제너럴라이제이션 같은 게 최소 인터폴레이션은 될 수 있기 때문에 이제 그런 조금 더 unstructured된 이제 실제 환경에서 실제로 쓰고 있고 또 그런 거를 잘 보여주고 있는 것 같고요. 그리고 말씀하신 대로 사실 이전까지 결과들은 대부분 게임 환경 같은 데서 왜냐면 리월드도 디파인하기 쉽고 스코어로
네.
시뮬레이션 자체도 쉬운 그런 환경에서 하고 있는데 사실 저희가 지금 그러니까 저희 연구실 내부에서도 그리고 제 개인적으로 이런 휴먼 인더 러닝이나 이런 걸 하는 이유가 그걸 좀 비욘드 하고 싶어서 그러니까 그러니까 실제로 이거를 RL을 쓰고 싶어도 막 리워드 디파인하는 게 너무 어려운 경우도 많고 이제 이제 스테이트를 정의하기 경우도 힘든 경우가 많기 때문에 사실 제가 이런 연구들을 해왔던 거고 저도 개인적으로는 그런 게임을 비욘드해서 어떻게 하면 더 RL을 이제 게임 이상의 더 인터레스팅한 도메인에 쓸 수 있을까를 좀 많이 이제 관심이 있고 또 그렇게 함으로써 이제 알파고처럼 되게 이제 어떻게 문샷 같은 정말 좋은 연구들이 이제 RL을 통해 또 나올 수 있지 않을까 생각을 하고 있습니다.
네. 감사합니다.
네.
또 질문 없으신가요? 네. 네, 더 이상 질문이 없으시면은 일단 여기서 마쳐야 될 것 같고요. 네, 오늘 마지막 발표를 해주신 이기민 박사님께 또 다시 한번 감사의 박수를 드리도록 하겠습니다.
감사합니다. 좋은 발표 기회 주셔서 정말 감사합니다. 네.
네, 좋은 발표 감사드립니다.
네, 감사합니다.
네, 네, 그러면은 이번 e-TEC Talks at SNU Summer 2021 그 컴퓨터 앤 VLSI 세션은 이것으로 마치고요. 또 연사분들께는 또 연락을 드리고 또 다음 이제 방학 때도 또 비슷한 행사를 계속 하려고 하니까 또 많이 참석해 주시면 감사하겠습니다. 네, 감사합니다.
감사합니다.